All right, diving in. Now you can see behind me I put some stuff on the board. That's one of the reasons I cut the last video a little short. I didn't want to keep going on that video, not just because it would make a long video, but because I had to set this up. And I didn't want you watching me set this up. And you're bored enough watching me. You don't need to watch me setting this up. Boring. All right, so this is problem number 3. If you look at problem number 3, you're going to see this set up for you. Now this setup is done because there are two different ways to solve heat problems. One way is what we used in the last problem, problem number 2. That's called the direct method. Problem number 2, we used the direct method. We directly looked up values in an HF, heat of formation chart, found those values, took the products, subtracted the reactants. Relatively not too bad. This method, however, doesn't always work for all chemical reactions. The reactions that we had in the last problem were combustion reactions. Combustion reactions happen very fast. They give off a large content of heat very quickly, which can be measured in calorimetry relatively easily. So that kind of a method, just taking values, looking them up, throwing them in, can be used when things happen very quickly. If the reactions happen very slowly over time, it doesn't work. We can't do that. Calorimetry is not going to work with that. We're going to have all kinds of problems, and anyways, we're going to have a lot of problems. So slow reactions don't work very well with that direct method. The other thing that doesn't happen if we have a lot of intermediate steps, and all reactions don't happen just in one direction like that. There are several intermediate steps that take place, and that can be a problem too. Another thing is if a reaction happens that includes a lot of other byproducts and what we're looking for, that could be a problem. What I'm trying to say here is sometimes we have to use a different method to solve for the change in the heat of the reaction other than just looking up values and plugging them in. I know that's the way we want to do it, and for a lot of times we can do it that way, but occasionally we can't. Let me give you an analogy. If you want to get to the second floor of a building, you have several ways you could do it. You could jump up through the second story window. Okay, you can do that. I have faith in you. Good, strong legs, just jump. You could take the elevator up to the 3rd floor and then take the stairs down to the 2nd floor. Or you can just directly take the stairs to the 2nd floor or an elevator to the 2nd floor. I mean, there's different ways of getting where you want to go. Bottom line here, too, different ways of getting heats of reactions. And sometimes we can use both of these ways, but sometimes we have to use the indirect method, and that is when we have reactions that just have some issues with that direct method. Okay. This indirect method is called Hess's law. Hess's law is essentially what Hess's law says. It doesn't mean you use indirect or direct, just make sure you get to the final reaction. Well, the indirect method we're going to use is called Hess's law, meaning that we can take partial reactions, add them together, and get an overall heat of reaction. It's really not that hard. We just have to make sure we just kind of get a little understanding of why it's happening and how we do it, which is relatively easy. So here I have a reaction. Let's just dive in here. Stop babbling, dive in. A reaction. Aluminum plus iron oxide makes iron and aluminum oxide. Let's determine the overall heat of this reaction. Is it exothermic, endothermic, and how much? Okay, so here I have written the overall reaction of what we're trying to find. Here I have written what are called 2 half reactions, 2 intermediate steps of the overall reaction. So this says that aluminum plus oxygen makes aluminum oxide. This is iron plus oxygen makes iron oxide. Don't freak out about the 1.5s. It's a balanced reaction. You can check it. Check it. Check. I miss hockey, okay? I miss hockey. So you can check and see those are balanced. Don't worry, the 1.5s are actually they're going to cancel out. Okay, you'll see that you can see that they do cancel out because they're not in the overall reaction, so they must be gone. So don't worry about the 1.5. This makes this makes this, and here, if we look these up, here are the heats of the reactions for each one of these partial reactions. Aluminum and oxygen making aluminum oxide releases 1,669.8 kilojoules of energy per mole. The iron plus the oxygen makes iron oxide, and that produces or releases because it's a negative, okay, releases the 822.2 kilojoules per mole of energy. But in this reaction, here's the overall reaction. We have to know what the overall reaction is to do this indirect method. We have to know what it is we're trying to find. So I'm trying to find out how much heat is produced or taken in during the production of the aluminum oxide. So this one shows production of aluminum oxide, This one shows the production of iron oxide, which isn't in the overall reaction. The iron oxide is actually a reactant in this reaction up here on top. It's a reactant. This reaction shows it as a product, and we produce negative 122 when we form it. But here it's not forming, it's breaking down. That means this reaction is backwards. Yes, it's backwards. How do I know it's backwards? Because it's on the product side here, and up here it's on the reactant side. So I'm going to switch this reaction. I'm going to make it in the correct direction, showing the breakdown of the iron oxide. Let's show it in the correct direction. So the breakdown of the iron oxide. So we have the iron oxide breaking down to form my 2 irons and that 1.5, which you're freaking out about, oxygens. Well, that doesn't look like a good 5. Come on, clean that up. There we go, a little bit better. Okay, so now I've got the iron oxide breaking down to form the iron and the oxygen. And that's what's going on up here. The iron oxide breaking down to form the iron, yes, and the oxygen. Well, where's the oxygen? Come on, you can see it, right? This oxygen here in the overall reaction cancels out with the oxygen here. Remember, these 2 reactions are called half or partial reactions. We add those together, we get this overall reaction. Let's check and make sure. This shows aluminum on the left, reactant, iron oxide on the left, reactant, iron on the right, product, and aluminum oxide on the right, product. So this combination here is the overall reaction. Okay, we reversed this reaction on the bottom so we can put the iron oxide on the correct side of the arrow. But when we reverse that, we got to reverse that. Over here, it was a negative 822.2. When it breaks down, it's going to be a positive, and the energy has to go in to break down that iron oxide. You want to break down iron oxide, you're going to put some energy into it. Okay, so this becomes a positive value, while this still stays the negative. All right, so what do? Just take these 2 and add them up. Just take the 2 values, add them up, and we'll have our answer to this problem. So we're just going to take these 2 values, add them together. You have negative 1,669 plus 822. So we end up getting, go ahead, do the math, you can do it. You should end up getting a negative. It still should be negative because negative wins here. It's a bigger number. Negative 847.6, negative 847.6 kilojoules per mole of the iron or the aluminum oxide that is formed. So what did we do here? Here we had to take 2 partial reactions, make sure we had them in the same direction, and I know that by looking at the overall reaction. So the overall reaction guides me with my partial reactions. If you look up these partial reactions, most chemistry books, college chemistry books, are going to have the formation of this and the formation of this in the back, and they'll give you these numbers. And then we would have to just make sure that we have the reactants in the right direction. I had to reverse this one because the iron oxide is a reactant, not a product. So I reversed the reaction, created my 2 reactions to mirror the top reaction, but since I reversed the bottom reaction, I had to switch the sign. So now you just go ahead and add those values. Just take those 2 values and add them up, and you can look up those 2 values in the back of a chemistry book I was saying, and go ahead and add them, and now you get the overall heat of the reaction. For this reaction, it's called the indirect method. I use partial reactions, so but I still come out with the correct value for the heat of the reaction. And this is an exothermic reaction because we lose that energy in the formation of the aluminum oxide. All right, so this means that we have 2 different methods of solving. The vast majority of your problems will be using the direct method. Okay, like we did, because we can usually look up these things. We have a lot of combustion reactions in chemistry that we can go ahead and use that direct method for. So you're probably asking, would you ask us one of these on the next academic adventure? Yes, I will. I'll ask you one indirect, and I'll ask you a direct, maybe a couple of directs. We'll do that, but we'll also have an indirect set up for you, just like this problem, and you go ahead and figure out what that answer is with the indirect method. Okay, so yeah, there we go.